Welcome back to the machine learning lecture. In this final video for this semester, we're going to learn about algorithmic fairness. As we've touched upon already in the previous videos, machine learning systems are being used in many different domains to automate complex decisions that involve humans or impact humans. And there are many different examples here. For example, often machine learning systems are being used to select different job applicants. There are systems which automatically look at CVs sent by applicants and decide which applicants are going to move on to the next stage in the process. There are also even systems that do live tracking as you're conducting an interview with an employer and keep track of your facial expression or your speech patterns and so on, and then report these scores to the employer, which can use to decide whether you get a job or not. There are many different machine learning systems used in the judicial and police system. For example, there are systems that predict which neighborhoods in a city are likely to have more crime, and then these predictions are being used to distribute police force. There's also machine learning systems for predicting which inmates are likely to commit crime if they're released from jail, and this is called Recidivism Prediction. And then, of course, these predictions are used to decide who gets parole or doesn't get parole. Of course, there are also systems to decide whether you get credit or not, whether you get a loan or not, and so on. And in these three cases, it's pretty obvious that the decision made by this system, made by the machine learning model, or maybe it's not only the machine learning model, but it's the model plus some other structures or algorithms around it, these decisions, whatever they may be, have a huge impact on the human involved. So we should be careful that they work as intended and they don't have some undesirable consequences and undesirable biases built into them. Of course, not only these systems, but other systems such as facial recognition, search, recommendation, machine translation, all of these other systems can be biased or unfair in subtle ways, which can, again, be potentially undesirable, and we have to look at them carefully to make sure they work as intended. And if you really basically try to look at all of these systems and try to quantify how they work and in which situations they break down, you'll find many, many different examples where these systems behave unfairly. To start with one example, which is relevant for Germany, it has been shown that the social network Xing consistently ranks less qualified male candidates higher than more qualified female candidates. And this obviously is not ideal, and it has to be fixed. Going back to the example of recidivism prediction, so predicting which inmates are risky or will commit crime once again if they're released from jail, we look at, for example, the errors that a certain classifier or model is making. And we see that this particular model, which actually was proprietary, we see that for high-risk inmates, so inmates who are predicting whether they're high risk if you release them from jail, the false positive rate, meaning I predict that you will be high risk, but you're actually not high risk, was much lower for the white inmates compared to the black inmates. So the false positive rate was almost twice as high for the black inmates, which then means that black inmates are less likely to get parole. And similarly, now, if you're predicting low risk, so the other way around, the false positive was higher for the white population or for the white inmates, which means that the white inmates are more likely to get parole in both of these cases. And we see that the error is not like a small difference. It's not only 0.5% or 1%, but it's almost twice as large in both cases. Looking at other examples, we have that facial recognition software, even facial recognition APIs by established big companies like Google, often don't perform as you would expect them on different subsets of the population. So it has been consistently shown that they have much lower accuracy on females with darker color, for example. You might also remember one scandal a couple of years ago where Google labeled automatically the image of a black person as a monkey, which obviously is not great, and there's many other issues that are coming into this one prediction, which of course has to be fixed. Other examples include search and recommendation. For example, if you search on Google or other search engines for African American sounding names or names which are typically associated with African Americans, you're more likely to get advertisements which are about arrests. Another very famous example is the bias found in word embeddings. So I don't think we've talked about this in the lecture, but basically word embeddings are a way to find a vector representation for each word in a sentence. So the goal is to take some text and then find 2D or 5D or 10D representations for each word in the text that captures the semantic meaning. So what you can do in word embeddings is say, okay, this is the vector representation for the word Germany, this is the vector representation for the word Berlin, this is the vector representation for the word Austria, and then you can ask, what is the closest word which is similar to the relationship? So if Germany to Berlin has some relationship, what is the closest word that is similar to Austria that has the same relationship? And turns out these kinds of systems automatically learn something useful, and the answer here will be Vienna. So the system will learn that Germany is to Berlin what Austria is to Vienna, and of course this can be used to do useful applications. But then if you ask what is the closest word, so what if man is a surgeon, a woman is question mark, so what is the closest to a woman which is similar as a surgeon to a man, and the answer will be a nurse. And of course this is not ideal because basically this system has picked up the bias in the data that men tend to be surgeons and women tend to be nurses, which is potentially undesirable, and we wouldn't want our system to be reasoning in this way. Maybe you also know have heard of the GTP3 machine learning or natural language model. This is a huge model trained with basically on a huge data set of text on the internet, and has 175 billion parameters. So you can think of it as a really massive neural network, one of the biggest neural networks ever trained. And what this system can do is pretty amazing. Basically, you can give it a prompt, give it a couple of sentences, and then hit autocomplete, and a system will generate a text which seems coherent and plausible, basically. Now, what happens is that these systems often exhibit racism or anti-Semitism, and there's no really easy way to fix them because they've been trained on a huge data set of everything that's found on the internet. So of course, the bias that's on the internet will get reflected in the system itself. And it's also not just a simple linear regression where you can tweak the weights to account for the bias. It's a huge model with 175 billion parameters, and there's no really easy way to get rid of the bias. So some question might be here, what actually causes the bias, or what makes these systems unfair? Well, one thing that we already hinted at is the training data itself. So if you only train a facial recognition system on faces from white people, of course it's not going to be able to generalize and perform as well on faces with a darker skin color. Or if you train it on text which has racist or anti-Semitic remarks, the system is going to pick up these associations that are in the data and use them to reason. For example, again, if you, let's say, creating a system for predicting which applicants should get the job, let's say you're doing your system internally, and you use the previous decisions you've made in the company to automate your decisions in the future. Then basically the labels that you're using as who gets in and who gets out are based on the decisions made by the humans in the company before. And if the humans making the decisions were biased, which is almost always the case because nobody is not biased, the final decisions made by the automated system will also be biased, because basically they've only learned to make the same associations that you've made before when you were making the decisions manually. And there was even again another scandal. So often there's many scandals when it comes to fairness and bias in machine learning systems. And in this case, it was with Amazon, where they tried to create a system that recommends CVs, and basically the system ended up recommending only male candidates because the company has historically only hired male candidates for certain software position roles. And beyond these simple ways in which the bias is obviously in the data, there's also historic and systemic biases. So, for example, certain population of people were historically disadvantaged, and because of that, they couldn't, for example, get economic advantages. They couldn't have good credit ratings, which is then reflected in the data, but that doesn't mean that they are inherently less likely to return the loan if you give them the loan, for example. Okay, so that was the training data. There is also other potential biases, which could be even due to random noise. So you can imagine that you have two neighborhoods, and then the first neighborhood, just by random chance, had more crime. And this was captured in the initial data. Now, if you train a machine learning system, and this machine learning system will going to pick up the fact that this neighborhood had more crime, so it will predict that it has more crime in the future. And now you decide that you're going to send police more often to this neighborhood. But by the fact that you send police more often to this neighborhood, you're more likely in the future to observe crime there. So you reinforce this bias that this neighborhood has more crime. While the first neighborhood, you decided not to send police there, so even if there's some crime happening there, you're not going to catch it in your data. And then if you see how this plays out over a long time, and then you look at the data, you'll see that this neighborhood has much more crime, while this neighborhood has no crime, only because you decided to focus on the first neighborhood. So in other words, what is measured is almost always equally important to what is not measured or what is not in the data set. There's other things which are also usually difficult. For example, in the United States, certain features such as race, gender, and sexuality are what is called protected, meaning when I'm making a decision whether you should get a loan or not, I'm actually legally not allowed to use the fact that you are from a certain race or from a certain gender. But unfortunately, simply ignoring these attributes is not enough, because there are many other features of you as a user that are highly correlated with these attributes. So the zip code where you live is highly correlated with your race. Your hobbies might be correlated with your gender or sexuality, and so on. So even if you hide these features, you don't show them to your machine learning algorithm, the inherent connections between race, gender, sexuality, and so on will be picked up by looking at the remaining features. Other issues might be with sample size disparity, where a machine learning model might tend to fit the larger group better at the expense of not fitting the smaller group as well. So let's look at one concrete example here, and let's say we have the red group, and this is how the red group is distributed. So here we have class 1, class 2, and these correspond to the red group. Now let's say we also have some members of the green group. They are distributed like that, and the green group is much smaller. Now, if we try to fit a classifier on this data set without distinguishing the red group from the green group, and let's say we try to fit the classifier that gives us the best possible accuracy, maybe we find this linear classifier over here. Now what's going to happen is that the predictions for the red group is 100% accurate, so all of these are on one side of the boundary and all of these are on the other side of the decision boundary, while the prediction for the green group is completely wrong. So it's completely switched on the other. So these ones are wrongly predicted and these ones are also wrongly predicted. And this is just a simple example, but this kind of effect, of course, happens in real-world applications. Because think about back to the loss that we're optimizing. So the loss says, I want to minimize the accuracy sum over all instances, meaning we treat each instance equally. And if there's no way to correctly classify all of the instances, like it is in this case with a linear classifier, we're going to trade off some accuracy in favor of the large group while hurting the smaller group. A different issue might be that of limited features. So the features for a certain disadvantage or minority group might not be measured as reliably. And here, of course, systemic biases come into play as well. Say systemic and historic biases. So given that we have all of these issues, the question becomes, what can we do about it? How can we take some of these abstract notions of fairness and mathematically formulate them so that we can include them as part of our machine learning systems? Unfortunately, currently, there is no consensus on what is the best possible way to mathematically formulate fairness, or whether even exists such a way to formulate fairness in an optimal manner. As I also mentioned in some of the previous videos, you can't even hope for to have only technical solution to this issue. So you cannot ever come up with an SVM++, which is automatically going to be fair and unbiased. However, we can do something. We can at least mitigate part of the problem by trying to incorporate fairness constraints into our machine learning systems. And here we're going to get some motivation. We're going to get an inspiration from fairness notions from the law. And specifically, we're going to look at two different fairness notions, which are disparate treatment and disparate impact. So disparate treatment is basically saying that the decision for whatever it is, the decision should not be based on a protected attribute. So whether you get a loan or not, whether you get a job or not, should not be based on your race, sexuality, gender, or other protected attribute. Of course, we already mentioned this in the previous slides that this is not ideal and doesn't work in practice, because even if you remove these features, there's other features that are highly correlated with these protected attributes, and just removing them is not going to fix the problem. The second notion of fairness from the law is called disparate impact, which is about the outcome. So now we're saying that the outcome should not disproportionately hurt or benefit people which belong to different subgroups. Or in other words, the outcome should be roughly the same or approximately the same for the different subgroups. Again, so these two notions, the disparate treatment is about the decision, and the disparate impact is about the outcome. And we'll see how we can take these notions from the law and formulate them in a mathematical manner such that they can be included in our machine learning models, they can be included as constraints in a constraint optimization problem, and hopefully help our classifiers to be, or our models to be more fair. We'll also see some other similar notions which are somewhere in between. Okay, now for the remaining of the lecture slides, we're going to use a single example which will help us kind of think through the different fairness criteria and how they're similar or different from each other. And this example is about loan prediction, or basically in this case we're a bank and we're trying to fairly decide who should get a loan. And in order to do this, we're going to predict which people are likely to pay us back. So we have some classifier. The classifier takes in the features of an individual, and these features could be anything, including these protected attributes. And we're going to predict whether this person will pay us back if we give them the loan. And then based on this prediction, we're going to decide these people get the loan and these people don't get the loan. And in this case, we assume that we only have two groups, the blue group and the orange group. You can imagine that this is a stand-in. This is an example of some protected feature. So this could be race, gender, or something else. But in this case, we have these blue and orange groups. Of course, the same ideas here hold to multiple different groups. And by now, treating these different groups similarly or differently is exactly where discrimination could occur, and our fairness, our loan classifier could be fair or unfair. So the underlying issue here, which makes everything tricky essentially, is that the distribution, the underlying distribution of who is likely to pay us back is different in the different groups. So if you look at, let's say, the orange group, these are the people who are really, in reality, going to pay us back if we give them the loan. And these are the people who are not going to pay us back if we give them the loan. And we see that these two distributions overlap here, which makes the decision tricky. But now if you look at the same distribution, so the people who will pay us back in the blue group versus people who will not pay us back in the blue group, we see that these distributions are, first of all, different from the orange group and also overlap a little bit more. So now, let's say you have some classifier. The classifier takes in the features of the individual, including all of their sensitive attributes, and outputs a score between 0 and 1, or between 0 and 100, it doesn't matter, which tell us how likely is this person to pay us back. So the higher the score, the more likely the person is to pay us back. And the way we're going to make the decision is we're going to simply threshold the score. So everybody above a score of 70 will get a loan, and everybody below a score of 70 will not get the loan. So we'll see that, let's say if we use the same threshold for everybody, a threshold of 50, we'll see here that the mistakes that we're doing in the case of the orange distribution are not as big, because there's not so much overlap between who pays us back and who doesn't pay us back, while using the same score for the blue group, we make much more mistakes. So don't worry, we'll look at this example in much more detail later on, but this already somehow gives you a hint that who pays us back and doesn't pay us back highly changes between the two different groups, which means that we might need to use different thresholds or different ways to decide between the two different groups. Okay, so in this example, the question is, how can we test? Let's say I have a loan classifier. Somebody has given me a loan classifier. How can I test if this classifier is fair? And before we do this, we have to establish what notion of fairness we're going to use. And there are different notions in the literature, but three of them are most popular. So there's the so-called group fairness notion. There's also individual fairness notion and counterfactual fairness notion. In this video, we're going to focus on the first one, but we'll also say one or two things about the others. So in group fairness, we're going to aim to treat all of the groups equally with respect to certain invariants that we're trying to enforce. So for example, we can say the same percentage of blue and orange people should receive loan. So regardless of what is the underlying distribution, who pays us back and who doesn't pay us back, 60% of blue and 60% of orange people should get the loan. So this is one notion. It doesn't mean it's the right notion, but that's one idea. You can also say that the false positive or false negative rate between the two groups should be the same. So what is the false positive rate? The false positive says I would repay, but I actually don't pay the loan back. and this is false positive. And we can say the false positive of the blue individuals should be the same as the false positive of the orange individuals. And there's many other notions of group fairness, and we'll look at them, all of these in detail. The idea behind individual notions is to say if two individuals are similar, they should be treated similarly. So you can imagine that you have one individual, it has a high dimensional feature vector, then there's another individual, again high dimensional feature vector, and the idea is here that if these two individuals are similar, they should have a similar prediction. They should both get the loan or both not get the loan. And of course here, what is very critical is how do you define this notion of similarity? Do you say that if we have different genders, that this doesn't matter? If we belong to a different race, this doesn't matter? How do you actually compute similarity between individuals? A more difficult, technically difficult notion of fairness is counterfactual fairness, where we basically try to reason what would have happened in a different world. So basically, what would be the decision if your features look exactly the same, but your gender is changed to the opposite? Or what would have happened if everything has been the same, but your race was different? And we would like, ideally, in both of these worlds, in the current world and in the counterfactual world, where gender, race, or whatever protected attribute has been changed, we want that the prediction, whether you get a loan or not, stays the same. And of course, this is difficult to model because changing one of these attributes from, let's say, male to female has a huge effect on all of the other features, and it's not easy to model what this counterfactual world will look like. But there's some work on this, and it's an active area of research. Okay, so in this video, we're going to focus specifically on group fairness, where we are trying to enforce different invariances between the two groups. And let's say we're working with d-dimensional features. So this could be the credit history, or your purchases, or your other history with the bank. And we denote the normal features, the non-sensitive features, with X. Then we also assume that there we have a single sensitive feature, like gender, race. So these are blue versus orange people, and this is denoted with A. In the remaining of the slides, we'll only assume that there's one sensitive feature, but of course in reality there's multiple sensitive features. So your race, your gender, your sexuality, all of these things influence in different ways whether you get a loan or not. And this can also be modeled, but for simplicity, we're going to focus on a single sensitive attribute. Now, what we're going to assume is that we have a classifier, a binary predictor, which outputs yes or no, which outputs 0 or 1. And this binary classifier is trained on both X, so the non-sensitive features, and A, the sensitive features. In some scenarios, instead of working directly with the binary classifier, we'll be working with a score. So you can imagine that you have a neural network that outputs a score between 0 and 1, and then to make the final decision, you threshold this score at some point, and everybody above the threshold is given the loan, and everybody below the threshold is not given the loan. But yes, depending on which notion of fairness we're considering, we're either going to look at the binary outcome or the score itself. And then in addition to these, we also have the target variable. So this is the ground truth, whether you're actually going to pay the loan back or not. And basically what we're going to assume is that these variables come from an underlying data distribution, and we're going to model them basically as random variables. So your features, your sensitive attribute, and your ground truth label, whether you will pay back the loan, all are IID essentially sampled, or maybe not IID, from some data distribution. And the notation that we're going to use is the probability of a certain outcome, the probability of the classifier predicting 1 or 0, conditional on the fact that your sensitive attribute has a value of A, conditional on the fact that you're orange or blue, we use this shorthand notation where we just write A as a subscript here. So the probability subscript A of R is just the probability of the event R, conditional on the fact that you belong to group A or group B. So as we've mentioned before several times, the naive approach, where you simply ignore or are blind about the sensitive attribute, doesn't really work in practice. And this is sometimes called fairness through unawareness. And basically the idea was here that instead of looking at both the normal features X and the sensitive attribute A, we're going to completely ignore the sensitive attribute and only compute the prediction based on the normal non-sensitive features. And this is intuitive, it's easy to implement, there's some support from the law, so not only in Germany with the General Equal Treatment Act, but in the US and other countries, there's actual legal requirements that you're not allowed to use these features such as race, gender, and so on to make decisions. But as we've already mentioned, this doesn't work because there's many other features which are highly correlated with the sensitive features. And usually our classifiers, our models, are powerful enough to uncover these correlations and use them to make unfair and biased decisions. So this doesn't work, and we're going to instead propose our first fairness criterion, which is called independence. And basically, the idea is pretty simple, and we're going to require that the outcome, the prediction, is independent, statistically independent from the sensitive attribute. So remember, X, Y, and A are all random variables. Let me go back to the slide. So all of these are random variables, which means that the binary predictor or the score predictor, the classifier, is also a random variable because it's just a function of other random variables. So now if we look at this random variable and this random variable, we can require that these are independent. So what does it mean that they're independent? That means that the probability of R and A should decompose into probability of R times probability of A. So there shouldn't be any dependence between these two. And this has many other names. It's called demographic parity, it's called statistical parity, it's also called group fairness. So in this lecture, actually, we're calling all three notions. So we'll introduce three different criteria, and we're calling all of them group fairness. But some people, or in some places in the literature, the first criterion is also called group fairness. Sometimes this is also called the Darlington criterion number 4, and so on. Okay, so how does independence look like for binary classification? Basically, what we're going to require is that for all groups A and B, if we have two groups, for the orange and the blue group, but if we have more than two groups, let's say we have 5 groups, all pairs of different groups of people, where the groups here are grouped by the sensitive attribute, that their prediction should be equal to each other. So requiring that R is independent of A is equivalent to requiring that the probability of predicting 1 for group A is equal to the probability of predicting 1 to group B. In this case, so in the example of the loan classifier, this means that the acceptance rate, so who actually gets the loan at the end of the day, should be the same. So 60% of blue people and 60% of orange people should get the loan. There's also some approximate versions of the same requirements. You can say, instead of really requiring here that we have an equality, we can enforce this in an approximate manner, where we say that the ratio of who gets a loan in the two groups should be close to 1. And we write this in with this formula, where we say that the ratio should be bigger than 1 minus some small epsilon. Or we can also write it as the difference, the absolute difference between the number of participants which get which get the actual loan, which are predicted as 1 in the first group, minus the second group, should be at most some small number epsilon. So how can we achieve independence? How can we enforce this criterion in practice when we're training a machine learning classifier? Here there are 3 different approaches which we can use. The first one is to do a post-processing step. So we learn our classifier on both X and A in a standard manner, which could be potentially unfair, and then we make some post-processing procedure which will decorrelate the prediction from the attribute, and will make sure that the same ratio of people get the loan, or the same ratio of people are predicted as class 1. A different approach is to incorporate this constraint, or maybe so either directly this constraint or one of the approximate versions of the constraints, as part of the optimization problem. So if you're doing, let's say, binary classification, you could say, I want to minimize the cross entropy subject to the constraint that both groups have roughly the same ratio predicted as 1. Or if you do an SVM, you can support vector machine, you can add this constraint as an additional constraint to the constraint optimization problem and then try to solve it. A different way is via pre-processing, or what is sometimes called representation learning approach. And we'll briefly talk about this on the next slide. So here the idea is we start with our original features, both X and A, and we map them to a representation Z. So you can think of this as a low-dimensional representation, what we talked about in the previous weeks. And then we only train the classifier on the low-dimensional representation. So take X and A, use some function to map X and A to Z, and then we'll learn our classifier only on Z. The trick here is to make Z in such a way that removes any of the information about the sensitive attributes. And there are different ways to do this. So, for example, there's a technical measure of information called mutual information, which measures how much information about one variable is encoded into a different variable. And one thing here we might be requiring is that the amount of information between the original features and the representation is maximized. So we want to retain as much of the original information as possible, while minimizing the information that Z, the representation, encodes about the sensitive attributes. So basically, it's like doing dimensionality reduction, but forcing the dimensionality reduction procedure to ignore any correlations or any information about the sensitive attributes. And here we can see one example. So we see that, let's say we've done here 2D dimensionality reduction, and if we do this naively, the different faces corresponding to different groups are naturally going to be clustered, which means that on this standard non-fair representation learning, the classifier could still use the sensitive feature. But if we run such an approach where we enforce that the representation Z has minimum information about the sensitive attribute, then we see that the faces belonging to different groups are all spread out, and we cannot really distinguish between them. And there's different variants. There's a fair principal component analysis method. There's a fair autoencoder or variational autoencoder, and all of these try to enforce that the learned representation doesn't or minimally encodes information about the sensitive attribute. So what are the pros and cons of this first criterion? Well, one thing is that it has legal support. There is the so-called 4/5 rule, which means that the ratio of applicants that gets, let's say, the loan should not be so the ratio, let's say, in other words, the ratio of applicants which doesn't get the loan should not be less than 4/5 of the group that gets the loan. So if we imagine we have multiple groups, different ratios between them get the loan, and this basically says the highest ratio and the lowest ratio should be at most 4/5 from each other. But the question is, what if the underlying distribution of who pays us back is really different? So what if 80% of blue are likely to pay us back and 43% of orange are likely to pay us back? By treating them equally, by giving them exactly the same ratio of loans, we might be losing profit, right? We are giving both groups equal amount of loans, which means that in the case of orange group, we're losing a lot. So in other words, independence is too strong, and not only that, it even rules out the perfect predictor. So if you know the ground truth, let's say somehow magically you know that everybody is who is going to predict or not, who is going to give back the loan or not give back the loan, and you use this perfect predictor, you will not satisfy independence. So independence is a notion which is too strong. And in addition to this, it's also subject to laziness. So what we can do is, take the blue group, find the optimal predictor for the blue group, which let's say maximizes profit, or however we select the optimal predictor. And maybe it turns out that now 70% of the time we give the blue people the loan and 30% we don't. Now what we can do for the orange people is just randomly really flip a coin and randomly give 70% of the orange people a loan, 30% not give a loan. Now, if you look at independence, this is satisfied. So 70 blue gets it, 70 orange also gets it, everything is satisfied, but we haven't really made the classifier fair because we're only predicting randomly for the orange group. So it's subject to laziness. And in order to fix some of these issues, we're going to go with the second criterion, which is called separation. The idea behind separation is that, again, we make the prediction independent of the sensitive attribute, but only conditional on the target, only conditional on whether you are actually going to repay or not. So the way we write down this mathematically is that the probability of R and A conditional on the ground truth variable Y should be independent. So whether I predict you will get a loan is independent of my sensitive attribute, conditional on whether I actually will repay the loan, conditional on Y. So one way to think about what conditional independence captures is via the following example. So whether you will get a fine is independent of the type of car you're driving, conditional on the speed at which you're driving. Let's write this down. So fine is independent of car, conditional on the speed. So if I drive with 300 kilometers an hour, whether I get a fine or not is independent of the type of car that I'm driving. But if I don't know the speed, if we don't condition on the speed, then most likely whether I get a fine and the type of car that I'm driving are correlated. So this is just to help you intuitively think about what conditional independence means. And I didn't mention this before, but this symbol is what we're using to denote that one random variable is independent of the other random variable. And then this symbol is, of course, here the condition. Okay, so separation also exists under different names. Sometimes it's called equalized odds, conditional procedure accuracy, avoiding disparate mistreatment, and so on. And in the case of binary classification, you can boil down this condition for conditional independence to enforcing these two requirements. Basically, it means that we should enforce that the true positive and false positive rate is equal for all groups. Again, so what is true positive? The true positive is if I actually going to repay and I'm predicted that I will repay, so how often do I get it correct that I will repay? while false positive is if I'm predicted that I will repay, but I actually don't repay. So how often I get the positive class wrong. And we want that these two rates, the true positive rate for A and B, should be equal, and the false positive rate for A and B should be equal. By the way, this also enforces that the false negative and the true negative are equal, because true positive is 1 minus false negative, and so on. So basically this means, if you think back to this confusion matrix, where this is predicted true or false, and this is actual true and false. So true, this is the true positive, true false, this is the false positive, and so on. Basically, if you have this confusion matrix of for the group A and the confusion matrix for the group B, we want that these two are the same. Sometimes this is too strong, and there's certain relaxations. One of these relaxations is the so-called equality of opportunity, which means now we don't really care about the false positive. We only want to match the true positive between the two groups, meaning we're only going to enforce this condition and we'll ignore the second condition. So in the case of a loan, we'll say that for all the people who will actually repay the loan, for all the people where y equals to 1, we want that equal ratio of them actually get the loan. And we don't really care about what happens to the prediction r equals 0, meaning those who don't get the loan. Of course, there's a equivalent relaxation where we don't only match the true positive, but we only match the false positive, and so on. And depending on which application it is, one of these relaxations might be more relevant or not. So the question is, how can we achieve separation? And to do this, we have to introduce the idea of the area under the ROC, or Receiver Operating Characteristic Curve. So think back to this classifier, which gives you a score between 0 and 1. And the way we were making a prediction before is by thresholding the score, saying everyone above the certain threshold gets the loan, and everybody below a certain threshold doesn't get the loan. So maybe something like this. Here is the threshold, and everyone above T is predicted class 1. Everyone below T is predicted class 0. So there's a way to measure how good a classifier is, which works in general. So this has nothing to do with fairness yet. And this is by looking at the area under the so-called ROC curve. So basically what we're going to do is we're going to try all possible thresholds. So a threshold of 0,01, a threshold of 0,02, and so on. Try all possible thresholds and look at the false positive and true positive rate. So we and plot them in this 2D diagram. So here we show the true positive rate, here we show the false positive rate, and then we try all possible versions of the threshold. So we try threshold T1 over here, compute true positive, false positive, plot it. Try threshold T2, threshold T3, and so on. All possible thresholds, Tk, and plot this curve. So in general, whenever you have some binary classifier and you plot this curve, you want that this curve is as high as possible. So basically you want that the area under the curve is as large as possible. If you think back to what the perfect predictor will look like, the perfect predictor will have a curve which looks something like this. And here is the true positive, and here's the false positive rate. So basically we want that the true positive is as high as possible at 100%, and the false positive is as low as possible at 0%. So this holds in general. You can take the classifier, plot the ROC curve, and then the larger the curve, the better your classifier is. So now what we're going to do is we're going to compute these ROC curves for the two groups separately. So we'll take the first group, group A, try all possible thresholds and compute the true positive and false positive rate, and we'll get exactly this curve. Then we take the second group, group B, again, try all possible thresholds, compute the true positive and false positive rate, and we'll get the curve. Now, looking at these two curves, the question is which classifier, which choices of thresholds will lead to us having the same true positive and the same false positive rate for both groups. And the answer is pretty simple. It's basically the part where the two ROC curves overlap. So this part over here is where the first corresponds to classifiers for the first group. This part over here corresponds to classifiers for the second group. And everywhere where these two overlap, we can achieve the same false positive and the same true positive rate. So one thing we can do is we can basically now pick some point, let's say over here, where the true positive rate and the false positive rate is the same for both groups. So here we see that both for the green curve and the blue curve, the true positive rate and the false positive rate is the same. So here be careful, just because they have the same true positive and false positive rate doesn't mean that we have the same threshold. So it could be that for the blue, so that here is a threshold of 0,1, here's a threshold of 0,2, here is a threshold of 0,3, 0,7, all the way to the end, while for the green group, the thresholds could look differently. So here it could be 0,3, 0,4, here it's 0,6, 0,9, and so on. So essentially, how changing the threshold gives you different true positive and false positive rate changes, basically. So for the green group, the threshold is, let's say, less spread out, while for the blue group, the threshold is more spread out, and so on. But nonetheless, we can find two sets of thresholds. So in this case, let's say 0,3 for the blue and 0,6 for the green group, such that the true positive and false positive rate is exactly the same. In this case, there's one more thing that you should keep in mind. So the way people, or the way, let's say, the bank will choose some of these potential thresholds might be driven by a different objective. So let's say we might want to maximize profit. And it could be that in the true positive cases, so we give you the loan and you actually repay back the loan, we make a profit of $10 or 10 euros because only interest rates are very small, so we don't make a large profit. But it could be that in the false positive case, so when I give you the loan, but you don't pay it back, the cost is much larger. So we lose, let's say, 200 euros. So it could be that the benefit for correctly predicting is much smaller than the cost for wrongly predicting. And typically in different applications, the cost benefit for true positive and false positive tends to be different, and these need to be adjusted. So now basically when the bank is selecting out of all these thresholds where true positive and false positive is the same for both groups, I'm going to choose the one which maximizes the profit. So basically I'm going to multiply the TP and FP rate by how much profit I'm getting and choose the one or like the two thresholds for the blue and the green group, which exactly give me the maximum profit. Here, just one more thing you should be careful about, but don't worry, this is just a technical detail. All of these classifiers that lie exactly on the curve, this curve or this curve, can be directly obtained by just changing the threshold. But if you want, for some reason, to obtain a classifier that's somewhere inside, so under the area, then you might need to do a randomization step, where you say, with probability 80%, I choose threshold 1, with probability 20%, I choose threshold 2. But this is just a small technicality, usually doesn't really matter in practice, and what the bank is going to optimize for is 2 thresholds that maximize the profit, in this case for some cost values for TP and some profit values for TP and some cost values for false positive. Okay, so then what are the pros and cons of separation? Well, for one, the optimal predictor, which was previously not allowed, where if we magically know who in reality will repay or not repay, now is allowed. And if you have the optimal predictor, this will indeed satisfy separation. It also penalizes laziness. So what we mentioned before, where you randomly assign people in one group to get or not get the loan just to match independence. Here this is disallowed because exactly this separation criterion will not be satisfied. However, although mathematically it makes sense, looking at the broader picture, separation might not be a good idea. Because basically, essentially what it does, it says people who are likely to pay the loan back now are going to get the loan. But it could be that one group is actually less likely to pay back the loan, but this is not really their fault, it's because of some systemic or historic reasons. But now by saying we don't care about those reasons, we only care about how likely you are to repay the loan, we're enforcing this gap, because now we're giving you the loan, which gives you some advantage, which makes you even more likely to repay the loan in the future, and so on. The same thing for the other group. The other group is not likely to repay the loan, so it doesn't get the loan, meaning it's even less likely to repay it in the future, so the gap between these two groups widens further and further. So while on paper this criterion looks nice, we have to look at the broader picture and maybe introduce something different. Okay, then the third and final criterion which we're going to consider is called sufficiency. The idea behind sufficiency is that again we enforce some conditional independence, but now we say that the target, the ground truth class, whether you actually repay or not, should be independent of the sensitive attribute conditional on the prediction. So previously we had that the prediction should be independent from the attribute conditional on the target, and this was called separation. But now we have the other way around, that the target should be independent from the attribute, sensitive attribute, conditional on the prediction. And this, just like the other criteria, also has different names: the Cleary model, the calibration within groups criterion, and so on. And basically enforcing this conditional independence is equivalent to saying that the given that I predict for you yes or no, or given that I have some score for you, a score of 0.7, all of the people which get a score of 0.7 in group A and group B, the fraction of those which are actually going to repay should be the same. So the fraction of people who will repay in group 1 should be the same as the fraction of people who will repay in group 2, conditional on the fact that they are assigned the same score. One other ways to think about this is that the score that we actually use to assign you how likely you are going to repay the loan should be reflective of the actual ability for you to repay the loan. And enforcing this condition is also equivalent to enforcing that for each group the following thing holds. And the way you should interpret this is that out of all people that get assigned, let's say, a score of 0.7, 70% of them should actually repay the loan. And out of all people that get assigned a score of 0.3, 30% of them should repay the loan. So here you should not mistake this for that 0.3 or 0.7 is your individual probability of repaying the loan, but the average probability that out of everyone who gets assigned a score of 0.7, 70% of them should actually repay. And this is a notion for how good a classifier is, which is called calibration. And actually it holds in general. So in general, let's say for the moment we forget anything about fairness, in general we say that a classifier is well calibrated if when the classifier says, so for all the instances where the classifier says class 1 is 80% likely, 80% of the time the classifier is correct. So in some sense, the probability of a certain class or the confidence of the classifier should actually match the reality of the predictions. And the simple idea is, instead of now saying I want to be calibrated overall, for all the instances ignoring groups, I want to be calibrated per group. So each of the groups individually should be calibrated on their own. And there are different ways to achieve calibration. So one common technique is the so-called Plat Scaling approach, where you just train a classifier in a standard manner, which outputs a score between 0 and 1, and then you post-process this score by feeding essentially a 1D regression to make the uncalibrated score calibrated. And then using this, now you can do Plat Scaling per group and make each of the groups calibrated. Just one more way you should think about this, just so it's easier to remember. So you can imagine that the x-axis is the score, so what your classifier is assigning, and the y-axis is the probability of actually belonging to the true class. And that what you want for a classifier to be calibrated is that the relationship between these two is a line, basically. So if I say, if I give you a score of 0.4, 40% of the time I should be correct. Right, and then now instead of enforcing this for the whole classifier, we enforce it for each of the groups. So what are the pros and cons of sufficiency? Well, for one, it's satisfied by the so-called Bayes optimal classifier. You don't really have to know what this is, but basically, essentially, this captures the notion of what is the best possible thing we can do. If we have clean data, if we can train the perfect classifier, what is the best possible thing we can do? And that's called the Bayes optimal classifier. And this classifier exactly satisfies this notion of sufficiency. What is also interesting here is that in order to make the prediction, we actually don't have to know the sensitive attribute. So if our classifier is has been already trained and has been calibrated, we don't really need you to tell us what the sensitive attribute is. And also it gives you an equal chance of acceptance. So an equal chance of success, you can think of it, if you're actually going to repay, the ratio at which you're going to get the loan will be the same for everyone who has the same likelihood to repay. But similar to what we talked about as a limitation of the separation criterion, it only looks at the current condition. So it only looks at how likely are you to repay the loan now, and ignores any of the historical or historical context or any of the future implications of what this might do. So again, as before, it could be that you are really unlikely to repay the loan, but this is not your fault. But if, again, this criterion doesn't incorporate this, and we might need some other ideas to make this work. So just to summarize what is happening in fairness, basically, since this whole subfield of machine learning has has become more and more, has become bigger and bigger in the last couple of years, people have been proposing many different notions of fairness in the literature. And all of them have this general theme that we require some sort of invariance or independence with respect to the sensitive attribute. So we looked at independence, which says the prediction should be independent from the attribute. We looked at separation, which we're conditioned on the target. We looked at equality of opportunity, which was a relaxation of separation. we looked at sufficiency, and so on. And there are many other different fairness criteria which are slight modifications or different versions of the same idea. So there's predictive equality, predictive parity, conditional statistical parity, and so on. One of the issues is that actually it's provable, you can guarantee, you can mathematically show that all of these or some of these notions are even incompatible with each other. So if you want to guarantee separation, you can never guarantee sufficiency. Or if you want to guarantee independence, there is a set of variables R, A, and Y such that predictive equality can never be satisfied. So not only we don't have a consensus, but we can't even say, okay, take all of them and try to satisfy all of them at once, because they are mutually exclusive with each other. Nonetheless, in certain applications, some of these might be useful, and indeed we should think about whether implementing them is a good idea. On this interactive website, you can explore how different fairness criteria lead to different decisions, and what does this mean for the fairness of one group of the other, what does it mean for the profit of the bank. So in this case, we are again working with the bank loan example. So ideally, the data should, or we want that the data looks like this, where everybody who doesn't pay, meaning this is called also would default on the loan, has a very low score, and everybody who will in reality pay has a very high score, and then we can find a nice clean separation between the two and be done with it. But unfortunately, in reality, the distribution of people who would not pay versus the distribution of people who would pay are highly overlapping. So finding one good threshold, finding one good classifier is not always easy. And here you can basically explore what happens as we're changing the threshold, what is the true positive, false positive rate, the accuracy, the error, and so on. And specifically now what we're going to look at is what happens if we have two different subsets of groups, the blue population and the orange population, which have different distributions of how likely they're going to repay. So the orange distribution, we see it's less overlapping, while the distribution of blue population between those who would pay and would not pay back the loan is more overlapping. And here we also assume that a successful loan, meaning a true positive prediction where we give you the loan and you pay it back, costs us or makes us $300, while an unsuccessful loan, so we give you the loan but you don't pay it back, costs us $700. So it's more expensive to make a mistake versus correctly giving you the loan. And in this case, everyone has some score between 0 and 100. So you can imagine it's a classifier that looks at the features, looks at the attributes, and predicts a score between 0 and 100. Or this could be between 0 and 1, it doesn't really matter. So now what we're going to explore is what happens if we're looking at different strategies. So one strategy that the bank can do is just going to say, I'm going to maximize profit. Meaning I'm going to choose such thresholds such that my total amount of profit is as large as possible. So I know how much a false positive makes me money. I know how much a false negative, I know how much a true positive is giving me profit. I know how much a false positive is costing me. So I'm going to just choose thresholds which are going to maximize the profit. Now, not only this is unfair, but actually the bank here is taking advantage of the fact that we have two different distributions. So it says for the blue population, I'm going to choose one threshold. For the orange population, I'm going to choose a different threshold such that my profit is maximized. So it's treating the two groups differently on purpose in order to maximize the profit. And this is obviously not fair. What we could do is we could say we are going to be group unaware. So we set this is fairness through unawareness, where we're going to say we forget the fact that the blue and orange population are different, and we're only going to choose the same threshold in both cases. And we choose the threshold again to maximize the profit. In this case, turns out the optimal threshold is 55. But we see that this is not ideal because only 30% of orange people have gotten the actual loan, and 52% of the blue people have gotten the loan. So there is some disparity here. We can implement one of our fairness criteria, and this is called here demographic parity, but in our slides we called it independence. And if you remember, independence basically said that the fraction of people who actually get the loan, regardless of their ability to pay it back, should be the same. And then now we implement this constraint and maximize the profit subject to this constraint. And we see that this is possible. Here we see both orange and blue, 37% of the orange and blue people exactly get the loan. But this is potentially not fair to the blue population because the blue population is more likely to repay the loan. So maybe we're disadvantaging them. Okay, let's try a different fairness criterion. Let's say we implement equal opportunity. So if you remember back to our slides, this was a relaxation of separation where we care about enforcing the true positive rate. Meaning, if I predict that you are going to pay back the loan, have you actually paid back the loan? So I want to enforce the fraction of true positive instances. And we see that this works again. And now the true positive rate for the blue population is 68 and is the same as the true positive rate for the orange population. But again, this might not be ideal because, as we said before, this is only based on the current situation and it doesn't take into account any historic or future feedback loops. Here I want to show you one more way to visualize what is going on with the different fairness criteria. And this example is based on real-world data. So what we're going to do is we're going to, again, look at each group separately, compute all possible thresholds or look at all possible thresholds and compute the true positive and false positive rate. So the fraction of people who are not going to default, who will actually repay, given that they were getting the loan, and the fraction of people who would not repay given that they're getting the loan. So false positive on the x-axis and true positive on the y-axis. And we're going to compute this ROC, this receiver operating characteristic curve, for all groups independently, and we're going to plot them over here. We see that the ROC curves are very similar, but there's also some parts in which they differ. And in order to better visualize what is going on, we're going to zoom in into this part of the figure, which is then shown on the right. And now what we're going to look at is how different criteria choose different thresholds for different groups. For example, if we choose the max profit criteria, it means we're just going to choose a different threshold for each group, maximizing our profit. So for the white group, we choose this threshold. For the other group, we choose this threshold. For the third group, this threshold. And for the fourth group, this threshold. And we see this is pretty unfair. For this group, we have a 40% true positive and less than 5% false positive, while for this group, we have 80% true positive and 1% false positive. So this group is clearly treated much better than this group. If we look at the fairness through unawareness, meaning we choose a single threshold, everybody gets the threshold of 66, and this again leads to different true positive and false positive outcomes. Because 66, or a threshold of 0.66 for the white group is over here, but a threshold of 0.66 for the Hispanic group is somewhere over here. So this is exactly what I mentioned also in the previous slide. If we look at the independence criterion, this means that the prediction of or who gets the loan is should be the same amongst the group, which now means that all of the thresholds are chosen such that always 50% of, in this case, the applicants get the loan. And finally, if we have separation, we want to choose a threshold or a classifier such that the true positive and false positive rate is the same for all of the different groups. Okay, so that was it for our discussion on fairness. Now, for the last few slides, I want to briefly talk about just a couple of slides talking about robustness to adversarial examples. And this is actually a topic which we'll cover in much more depth in our follow-up lecture, Machine Learning on Graphs and Sequences, but I mention it here because it's very related to privacy and fairness. And also because at least some of the researchers in our research group are working on this topic. They're working on robustness, and if you're interested in doing maybe a master thesis, you should feel free to reach out to us. Okay, so recently, researchers have figured out that almost all classifiers are vulnerable or sensitive to adversarial examples. What this means is you can take the input, slightly modify it, add some small, carefully created noise, and then the classifier will misclassify that input. And this is here shown on the slide, shown on the figure on the slide. So let's say that we have some classifier, maybe it's a linear regression classifier, logistic regression, maybe it's a deep neural network, it doesn't really matter. Let's say we have an image classifier, and then we take this image, we pass it through the classifier, and the output is panda, meaning it's correct. Now, what you can do is you can add a very small amount of noise, so notice here the very small multiplier, to this image, and take the resulting noisy image and again pass it through the classifier. And in this case, the classifier will make a wrong prediction and will predict that this image is a gibbon. So if we look, we as humans, if we look these two images with and so without and with the noise, to us they look exactly the same. It's pretty clear that in both cases we only see a panda. But apparently to the classifier, these two images look completely different. And this happened because we added some small but carefully created adversarial noise. And this noise is so small that we as humans cannot even see it. And not only that, but the situation is much worse. So the network thinks that this is a panda with a confidence of 60% and thinks that this is a gibbon, so it's wrong with even higher confidence. It's wrong with a confidence of 99%. And the question is, why does this happen? And turns out this actually happens for many, many different classifiers. And there are many different examples for image data, for text data, for audio data, and so on. One interesting example is where you can actually 3D print physical glasses, and then when you put on these glasses, you're going to fool different facial recognition systems. So in this case, we have this person who is wearing these specially created adversarial glasses, and now when you take this image and pass it through a facial recognition system, the system will say that this person is this actress, which obviously is wrong. And here there's two more examples when the people are misclassified as being completely different people because they're wearing these adversarially created glasses. There's even different examples which might be more dangerous in real life. So you can imagine that you have a system which looks at the road signs, where it's a stop sign, a speed limit sign, or something else, and is trying to classify them. And maybe this system is part of a self-driving car or something like that. Now, it turns out what you can do is you can create specially created adversarial stickers, such as these ones, and you can place them on these stop signs, and this will cause the classifier to misclassify it from a stop sign to a speed limit sign. And of course, this is pretty dangerous because you think that your classifier is perfect, it has 100% accuracy, but in reality, by adding these small stickers, the classifier could be completely fooled. It could be completely manipulated. And these kinds of examples are everywhere, basically. So there's so many different ways to trick or manipulate your classifier. There's an interesting example where you can add almost imperceptible audio signal into, let's say, a song track. And then when you play this song, even though we as humans cannot hear it, personal assistants such as Alexa can detect it, and it will trigger in the background some sort of action, let's say like buying some product automatically. And of course, this can be misused to cause damage. You can also think about different classifiers, such as maybe a spam filter. So you have a classifier which tells you whether the email is spam or not. And here again, the adversary is trying to manipulate the system, is trying to add specially crafted words, sentences, or question marks, and so on, in order for the classifier to be fooled and say, oh no, this is not spam, I'm going to let it through. And really, the fundamental reason why classifiers are sensitive to adversarial examples is that they don't really generalize to unseen data. So if I train my stop sign classifier on some data set, usually I collect some small amount of data, split it into train, validation, and test, train on the train set, pick my hyperparameters on the validation set, and then finally evaluate on the test set. But this data set doesn't really capture all of the possible variations that you can encounter in practice. So in practice, maybe the weather can be foggy, maybe it could be rain, there could be rain or no rain, maybe there's different lighting conditions and so on. And usually there's no really a good way to create a data set that captures all of the possible variations in the data. And because the classifiers are trained essentially on a limited fraction of the data, or a limited subset of what actually you're going to experience in practice, this can be taken advantage of, and you can create this carefully created noise, which will then cause the classifier to behave wrongly. Then, of course, the question becomes, what can we do? Can we somehow detect these adversarial examples? And turns out, yes, in some cases you can do, but it's not always easy. And there's this arms race that's happening between the attackers coming up with a better attack, then you come up with a defense to counter that attack, but then the attackers again beat that defense, and so on. There's always this arms race between attackers and defenses. But still, we should be carefully thinking about these, because if we actually want to use classifiers in the real world, we have to make sure that they are not easily manipulatable by motivated adversaries. And one notion here that does help us is the notion of certified robustness or certifiable robustness, which is essentially a mathematical guarantee that there is no adversarial example. So you can say, I have my input image, and then I can mathematically check all the possible images which are within some epsilon distance of my starting image. And if I can mathematically prove that all of these images are correctly classified, then I know that my prediction is certifiably robust. But of course, you can imagine that this is pretty difficult, because given an image, there's infinitely many other images which are of distance 1 or distance 0,2 to this image. But still, there are ways that you can relax this problem and still solve it in practice. The other notion here you should keep in mind is that even though in your application there is no adversary, maybe you're running some classifier internally in a company and you trust everybody who has access to the classifier, you should still think about adversarial examples, because it could be that they're just naturally occurring noise which is going to cause the classifier to mispredict or to misbehave. And then essentially what adversarial examples are quantifying is what is the worst case thing which can happen to your classifier. So to summarize, this week we looked at different aspects beyond accuracy which turn out to be very important when you use or deploy machine learning systems in practice. And this included privacy, fairness, reliability or robustness, explainability, and so on. And here I want to highlight one particular thing. Often there's this idea that just because decisions are based on data, they're somehow automatically more fair or better. If you have an algorithm which is making decisions, people typically think that this algorithm must be better than a human making the decision, because the humans are biased and the algorithm is not biased. And this idea is false. As we've seen, the data itself can contain biases. It could be that the data contains is not representative of all the populations, or the data contains anti-Semitic messages or something like that. And just because we're using data to make our decision doesn't mean that the decision is accurate or fair. And moreover, not only the data, but even the algorithms that we are using can be biased. So if we say that we are minimizing the cross entropy and we treat each of the individuals, each of the instances in our data equally, as we saw before, it could be that we disadvantage the minority group in favor of the majority group. So even if the data is clean, it could be that our choice of a loss function actually introduces some unfairness or bias. So just because we're using decisions based on data doesn't mean that our decisions are fair or reliable or accurate. So here we specifically talked about differential privacy, which allowed us to take arbitrary computations, arbitrary functions, and make them differentially private in the sense that they will not leak too much sensitive information about the instances or the individuals in that data set. And the way this worked is by taking the function, computing the output of that function, and then adding noise, which is proportional to the sensitivity of that function. However, here there's again one more disclaimer. Just because some computation is differentially private, it doesn't mean that you have absolute privacy. So it could be that somebody knows all of the information about your neighbor, and just because your behavior is highly correlated to the behavior of your neighbor, they can deduce a lot of information about you. So just because some computation on a data set is differentially private doesn't actually mean that you have complete privacy. We also talked about algorithmic fairness, so where we try to enforce certain different invariances in the classifiers, such as same true positive rate, same false positive rate, and so on, in order to make decisions or predictions which are more fair. And yes, this helps to some degree, but as we talked about before, only having technical or algorithmic solution is never really the entire solution, and we need other social, legal, and political interdisciplinary effort in order to advance fairness. And it's always really difficult to foresee what, let's say we implement the separation fairness criterion. It's pretty difficult to say what kind of effect this will have in 5 or 10 years, because people will know that we've implemented the fairness criterion and they might modify their behavior, which then changes everything. What is also interesting is that there's some interplay between privacy and fairness. So let's say we're doing differential privacy, which means that we're computing the mean of some population, and then when, in different cities, and then we're adding some noise. Now, what could happen is that this could work really well for really large cities because the amount of noise is not as big and there's enough people to still get a good estimate. But now, if you do the differentially private computation in a very small city, the amount of noise you add might be so large that the information is no longer reliable. And then if somebody is using this information to decide whether this small city needs a donation or something like that, it could be disadvantaged because now we've made it differentially private, but we've made it less fair. And in general, all of these issues, privacy, fairness, explainability, reliability, are interconnected, and improving one might damage the other one and the other way around. Okay, so that was it for our lecture on advanced topics, where we cover differential privacy, algorithmic fairness, and adversarial robustness. On the behalf of the team and our research group, thank you for attending the lecture, and thank you for your attention this week. Good luck with your exam.